So this is part 2 for graphing rational functions. So here's an example here. F of x is equal to 3x plus 3 all divided by x plus 1. And really, again, before we look at the asymptotes that this rational function may have, let's just look at the wholes, because again, it's important to remove those common factors before, or else we may confuse them with vertical asymptotes. So if we look at this, right, clearly we can factor out the numerator, right? We can write this as f of x is equal to 3 times x plus 1 all divided by x plus 1. And so looking at this, we can remove, right, x plus 1, because x plus 1 is a common factor in the numerator and in the denominator, which is the definition of the whole. It's something that it's a factor that's common in the numerator and the denominator, and thus can be cancelled. So you see that x plus 1 is that factor. Now if you want to find the whole, what you're really doing is you're setting that factor, that common factor, to 0. So if we set this to 0, we get -1, and that makes sense. The x-coordinate of the whole must be -1, because if you substitute -1 here in the denominator, you get that undefined value, and really this alludes to the removable discontinuity. And so the whole is actually, you'll see later as I graph it, it's going to be like that. So that's the visual representation of the whole. So we know its x-coordinate being -1, right? Now how do we exactly determine its y value? Well, the way how you do it is that you remove those common factors from the rational function. So x plus 1 and x plus 1, we really remove those factors, right? And then whatever we're left with, we substitute that value of x back into the equation. So say we had something like, after we removed x plus 1, say we had something that was like f of x is equal to, I don't know, 3x squared. Say we had this after we removed x plus 1. Really, we're going to substitute this -1 into this equation to get our y value, right? That's how we're gonna do this. And in this problem itself, we don't have anything like that. If we eliminate the factors out, we are left with f of x is equal to 3. And if you think about this, this is just a line. I mean, if I graph this, this is just a line, a horizontal line that you take any x value, the y value will be 3, right? You take any x value here, the y value has to be 3. So clearly, we should know by now that the whole, the exact point for the whole is -1 comma 3. And again, the basic idea is that you have the function, you factor it out, you take all the factors that are common and you remove them, you set any one of the factors you want to 0, and you determine the x value, right? And in order to find the y value, you substitute the value back into the equation, and making sure that your factors have been removed, the common factors have been removed, and then you get the point for the whole. So in this case, the whole is -1 comma 3, right? That's your whole. Now, looking at the vertical asymptote, right? I mean, it will make sense for you to say that, oh, x plus 1 is in the denominator, but again, we really, in this case, the vertical asymptote is non-applicable. And the reason that it's non-applicable is that you had removed the x plus 1 because x plus 1 was common with the same factor in the numerator. So in order for a vertical asymptote to exist, there must be a distinct factor in the denominator, and clearly in this problem there's not. Therefore this is non-applicable. Now with the x-intercept, again, that's the value of x when y is set to 0, which essentially means that the numerator is 0. Now if the numerator is 0, that will be at the point -1 comma 0, right? You may put that as your x-intercept. However, once you graph it, you will realize that that is not really possible because your whole was at -1 comma 3. If your whole is at -1 comma 3, and that's where the function is undefined, how can you have a point at -1 comma 0 really? So if we for now, let us just say that x-intercept is not applicable, because again, you have that point here, you have -1 comma 3 where there's a hole, where there's that discontinuity. So you really should not look at the the x coordinate and just say and make that assumption that negative 1 comma 0 is your x-intercept, because you have negative 1 in common here with the whole. So looking at the y, and again, just by observation, you will see as you practice more problems that the whole will always be the dominating factor. If there's a hole at that point, your x-intercept or your horizontal asymptote or any other such will be disregarded. So you always look at your hole first to see if it exists, and if it exists, then this factor will dominate all the other factors. So negative 1 comma 3 is your hole, however your x-intercept is non-applicable. Now your y-intercept is a value of y when x is set to 0. Now that in this case, you just substitute that in, so you get 3 over 1. That's just 3, so we have 0 comma 3. And your domain, right, is a set of all real numbers such that x is not equal to negative 1. And the reason why it's not equal to negative 1 is because there's that discontinuity at x is equal to negative 1. Therefore, it's all real numbers except x is equal to negative 1. Now, if we graph this, right, if we graph this function, we have many values that are non-applicable. I know I forgot the horizontal asymptote, but you will see why here in just a second. So if we graph this function, we don't know much. All we know is that there's a y-intercept at 0, 3. And then we also know that there's a hole at negative 1, comma 3. There's a hole at negative 1, comma 3. Now a hole looks something like that. And looking at this function, we know that we had simplified this to f of x is equal to 3. And really what that means is essentially you've taken any value of x, you substitute that value in for x. That x plus 1 and that x plus 1 are offsetting each other, right? That means that you can put 10, 11, or anything. If you place 11, 11 plus 1, 12, and then you have 11 plus 12, 11 plus 1, that's also 12 in the denominator. So if you have 12 here and 12 here, they're just going to cancel off. They're going to cancel off. So if they cancel, then really you have 1. You don't have anything, right? That really means that you place in any value of x, you're going to, for almost all the points, you're going to get the y value of 3, except at the point negative 1, because there's that hole here. There's that hole here at negative 1 comma 3. So that indicates that really if you were to graph this, it's just going to continue going. And so it just gives us that equation of y is equal to 3. However, there's no vertical asymptote, but there's that hole at negative 1 comma 3. So that's the idea, and that's why I was going to say that the horizontal asymptote is actually none. You may be confused by looking at it and saying, oh, well, degree is 1, therefore we can do a over b, 3 over 1 is 3, therefore that must be the horizontal asymptote. However, if you look at this carefully and you graph it, you will see that after simplifying and removing these common factors and graphing y is equal to 3 with the removable discontinuity or the hole, there's no horizontal asymptote because we don't have that asymptote which the graph is approaching. We just have this hole here. So our function being graphed looks like this. So again, in the next lesson, again, I'll be going over more examples of graphing rational functions. So thanks for watching.